Welcome, class. Today we are going to start our discussion of Chapter 3. In Chapter 3, we're going to be talking about two key concepts in the study of chemistry, and that is matter and energy. And first, today's lecture, we're going to talk about matter, and our next one will focus on the idea of energy. So, first things first, to define matter, right? It is simply anything that occupies space and has mass. So another way you might think about that is it has mass and space. Another way to think about space, right, is volume. So anything that has mass and volume is matter. Now, as we saw in Chapter 1, right, matter is ultimately composed of atoms. And as a reminder, atoms, again, are these submicroscopic particles that are the fundamental building blocks of matter, right? That's part of their definition. And also are what we call the smallest identifiable unit of an element, which we'll get into in more detail in Chapter 4. Now, these atoms will sometimes combine with each other to form what we call molecules, right? Remember, molecules are simply two or more atoms chemically joined to each other in a specific geometric arrangement, or they have a specific shape. Again, this will also become known as the smallest identifiable unit of what will be called a compound. And we'll, again, talk more in detail about compounds in a later chapter. So when we generally think about matter, we can think about organizing it in one of two ways, by what we call its state of matter or by its composition. So first, let's talk about states of matter. This is something that almost everybody is familiar with. We have three primary states of matter. We have solids, we have liquids, and we have gases. So a solid, there are actually two types of solids, which we can think about. We have what are called amorphous solids. These are solids that don't have any long-range repeating pattern or long-range order. Glass is an example of an amorphous solid. Certain plastics, things like butter, lard, right? These things that are solid but do not have a defined pattern or defined order, if you were to think about the atomic structure. Then we have crystalline solids, which do have a long-range order. And examples of this would be something like diamond, which you see here, right? And we see diamond is a series of carbon atoms bound to four other carbon atoms. And we see this pattern repeat over and over and over again, giving it a very ordered arrangement. Other compounds, other types of materials that fall into this, things like sodium chloride, or salt, right? It would be another example of a crystalline solid. And then, of course, you can also exist in the liquid state or the gaseous state. So if we look a little closer at these three states of matter and how do they compare to each other. So a lot of these things will be familiar to each other, and so I'm just going to quickly sort of re-go over some of these if you may be unfamiliar with them. So if we think about a solid, first of all, solids are essentially the atoms are fixed in place. Now, they're not stationary, they are vibrating, but it's kind of like they're connected by springs. They're just sitting there sort of bouncing back and forth. So they are very close. The atoms or molecules are very close together. They have a defined shape and a defined volume. And that they are incompressible, meaning the atoms or molecules cannot be squeezed any closer together. Now, if we compare that to a liquid, the atoms or molecules that make up a liquid are free to move around relative to each other, so they can move around each other. And so this allows us, if we think about the difference between that we know between liquids and solids, right? This is why we can pour solids, we can swirl solids, it can flow, right? It can change its shape, right? These are things that indicate some freedom of motion. Now, the atoms or molecules are still very close together, but as I just said, they have an indefined shape. They can change shape, but they do have a defined volume, right? If you have, 1 liter of a liquid, no matter, you can put it in a square container, a round container, it's still 1 liter. And just like a solid, it's incompressible. Now, finally, we have a gas. Gases have, if you will, unlimited freedom of motion, right? They are free to move relative to each other, so they can go apart from each other. So when we have a sample of gas, the atoms or molecules that make up that sample are actually very far apart. So when we think about a sample of a gas, it is mostly empty space. So there's a lot of empty space in a gas sample. For this reason, it not only has an indefined shape like a liquid does, but it also has an undefined volume. In other words, one of the things that we think about for gases is they will expand to fill the volume available. And for this reason, they are the only state of matter that is compressible, meaning you can squeeze the atoms or molecules closer to each other. So because of all the empty space, the atoms can move closer, be squeezed closer to each other, and then re-expand to move further apart. So it is the only compressible state of matter. So the second way that we can organize matter is based on its composition. So what is it made of, right? So we have 2 basic types of composition. We have pure substances and we have mixtures, right? So a pure substance is what we call just one type of matter, makes it up. So there are 2 types of pure substances. We have elements, right? And so elements are materials that cannot be broken down into simpler substances. So these are the most basic of materials, right? And as we referenced a little earlier, the basic building block of an element is going to be atoms of that element. And another key idea about elements that we'll expand upon next chapter is that all of the known elements are found on what's known as the periodic table of elements. Now, the other type of pure material is a compound. And so a compound is simply 2 or more different elements in a definite fixed proportions. So a compound is 2 or more different elements combined in a definite fixed proportions. So a couple of things that we should expand upon this a little bit. So as I mentioned on a previous slide, the simplest unit of a compound is a molecule of that compound. Now, we should also understand that there are some different ideas with the term molecule. So molecule really has two different meanings. One of them is what we're talking about here, and that is it's the simplest unit of a compound. We call that a molecule of that compound. But there's also the definition of a molecule that it is simply two or more atoms chemically bonded in a specific geometric shape. So, in other words, to be a molecule, by that definition, you don't need to have different kinds of elements. But in order to be a compound, you do have to have at least two different kinds of elements. So let's look at an example here. So, whereas water, right, is a compound, and that water compound is made up of molecules of water, right? If I have the material O2, right, so this is how oxygen gas exists. This is not a compound, but this would be considered a molecule of water because it's more than one atom. So, of oxygen. Oxygen is made up of molecules of O2, but this would not be a compound because it only has one kind of atom. So we have to be a little bit careful with these terms, and especially since the term molecule can kind of be used in at least a couple different ways. So those are pure substances. A mixture is simply two or more pure substances, right? Two or more elements or compounds that are mixed together and can be separated from each other. So, a mixture, a combination of two or more elements or compounds that are combined, you get a mixture. It can also be separated back into those individual components. Now, a mixture can either be heterogeneous, which means the composition varies within the mixture. So if we look at this heterogeneous mixture of oil and water, right? In some parts of the mixture, say up here, we have a lot of oil and very little water would be there. And down here, we have a lot of water, very little oil would be there. So heterogeneous. Right? Other examples of this might be the mixture of sand and salt, or mixture of any two solids, in fact, right, would be heterogeneous. They would not be perfectly, you would have different compositions in different spots. You can also have hetero homogeneous, right? This is the composition is the same. Throughout. So a homogeneous mixture actually looks like a pure substance, right? Visually, it looks like it's all the same. And it is in some ways, right? It is the same composition everywhere, but if we were to look at the atomic level, what we would see is that it's made up of different materials. It is in fact a mixture. So this tea with sugar, right, is a mixture of water, sugar, and other compounds, like caffeine and so forth, that would come from the tea. So it is a mixture of multiple, in this case, multiple compounds. But it's homogeneous, so the composition is the same everywhere throughout that mixture. Now, we also said that the mixtures can be separated into their components. So there's different ways we can separate these depending on what it is. Sometimes we can do things like filter to separate, or we could do something called a distillation, which separates things based on their boiling point. So if something is easier to boil. It boils at a lower temperature. When we heat it up, it'll turn into a gas first, and it'll be separated in that way. So there's various ways that we can pull these components back apart. So mixtures can be separated back into their individual components. Now that we've looked at matter itself, now what we want to look at is what we call the properties and changes of matter. So what are some of the properties of these different types of matter, and what are some of the changes that matter can undergo? Now, in the big picture, these can be grouped into two big sort of groups. We have physical properties and changes, and we have chemical properties and changes. And so, what's the difference? So, first of all, a physical property can be observed without changing the composition of the matter. So these would be things like, if you want some example, these would be things like odor, taste, boiling point, density that we talked about in the last chapter, solubility, and so things that we can observe or measure without changing the composition of the matter, without changing what it is, in other words. And physical changes sort of go along with it. These are changes which do not change the composition. So in a physical change, the composition does not change. So these would be things like changes of state. So changing between the different states of matter, melting, freezing, vaporizing, etc. These do not change what it is, right? They don't change the composition, right? If I boil water, it is still water. It's just in a different state. Or another big one that we look at is dissolving. Right? As I dissolve salt or sugar into water, right, it is still salt and sugar, right? The components are still there. And as a result, right, we could separate them back out. Right? They're just going into a different form, right? Now, we can contrast that with chemical properties and chemical changes, right? So chemical properties can only be observed by changing the composition. So these are things like flammability. In other words, does it burn? What is its acidity? Or corrosiveness? We can only visualize or see these by changing what the material is. So the only way that we observe the flammability is by burning something. And once we burn it, it is no longer the same material, right? Think about burning a piece of wood or burning, anything, right? It is no longer that same material after you've burned it. It has changed composition. And that's the idea. So cooking is often, things that we associate with chemical properties, right? When we have these sorts of things. So that means things that are classified as chemical changes are changes where the composition does change. These are often referred to as chemical reactions. Is usually how we'll refer to them as we go through. So when we think about chemical reactions, these are chemical changes, right? The composition, the matter that is present is different at the end than it was at the beginning. So when we're doing things like burning or corrosion, or what we example would be rusting or bleaching, right? Something. These are examples of chemical changes or chemical reactions. Now, regardless of the type of change that we're undergoing, we always obey what's called conservation of matter, which basically says that matter is neither created or destroyed in a chemical reaction or chemical change. So this is what we call conservation of matter, or sometimes referred to as conservation of mass, because mass is conserved, right? If we burn something and we capture all of the products that we get when we burn that, the mass will be exactly the same as what we started with, right? We have conservation of matter, or conservation of mass within a chemical reaction or chemical change. So now that we've talked about matter and different ideas surrounding matter, next class we will think about energy and how we can think about energy getting involved in these physical and chemical changes.